Polynomials, complex numbers. I've mentioned this before, but it is kind of an important point. If you're looking to factorise a polynomial or solve it, if you notice all the coefficients are real, then you know the solutions, or the complex solutions, will always appear in conjugate pairs. So what does this mean? If you've got a polynomial of degree n, you can always factorise it down to be a mixture of quadratics and linear functions. Now, the quadratic may or may not be able to be factorised. Now, obviously, if the roots are complex, then it won't be able to be factorised over the real numbers. But if we factorise over the complex field, then we will get linear factors, and there'll be n of them, whatever the power is. So a quadratic will have 2, a cubic will have 3, and so on. Now, what this means is every odd-ordered polynomial must have a real solution. Because if the complex ones are occurring in pairs, then that leaves at least one left over that must be real. Now, that can come in handy. So here, start with a simple one, a quadratic. X squared plus 2x plus 2. You know, what multiplies together to give 2, adds together to give 2. You're going to struggle to find some numbers that do that. But what I can now do, I'll turn it into the difference of two squares. Well, in this case, it's the sum of two squares. So complete the square. But that 1, of course, we can turn into minus I squared. And we get x plus 1 plus I, x plus 1 minus I. So that's it factorised over the complex field. Here's a quartic, but it's a quartic that looks like a quadratic. So we can act with that one and go, that's going to be z squared minus 3, z squared plus 4. Well, the z squared plus 4, if I'm just dealing with real numbers, won't go any further. But the difference of two squares in the other one, I'll get z plus root 3, z minus root 3. So I'll factorise it over real numbers there. If I want complex numbers, I'd keep going. Well, the z squared plus 4 could be z plus 2i, z minus 2i. And the solutions, well, plus or minus root 3, plus or minus 2i. So it all depends how they're asking us to factorise or solve the equation, whether they're looking for complex ones or just the real ones. Okay, our factor theorem, we know that one. X minus a is a factor of the polynomial. We know polynomial a equals 0. If it was ax minus b, then what we'd be substituting is b divided by a. So the constant divided by the coefficient of x. That would be how we're looking for solutions with that one. We have a cubic. They've told us to factorise, but it's a cubic. So it's of odd power. I know there's a real solution. So the first thing to do is to look for the real solution. Now we know that it must go into 5. Well, that makes life easy because 5 is a prime number. Could be 1, could be 5, could be negative 1, could be negative 5. But it's not monic. So we could also have 5 on 2 minus 5 on 2, a half minus a half. So logically, the first one you would try would be minus a half. I mean, it's logical. Oh, look, it works. That was lucky, hey? All right, now, of course, in reality, I wouldn't have tried that one first. I probably would have tried 1 first or something easy. But eventually we get a solution. So I now know 2x plus 1 is a factor. I can complete the factorisation. And now I've got a quadratic. Well, does that go down? Multiplies together to give 5, adds together to give negative 2. No, it doesn't sound like a simple one. So I'll complete the square on that one. I'll get x minus 1 squared plus 4. No, they are not absolute value symbols, by the way. For some reason, PowerPoint has chopped off the top and the bottom of the brackets. And so we get 2x plus 1, x minus 1 minus 2i, x minus 1 plus 2i. A quartic. We have two rational zeros. Find them and then factorise. And now it's got to go into the constant. So that's 3, 1, negative 3, negative 1. But it's also got a coefficient of 4 on x to the power 4. So I could have 3/4, I could have 1/4, I could have 3 on 2, I could have 1 on 2, I could have all the negatives of those. Again, let's pick something logical to start off with. Yeah, half. Oh, it works. Oh, geez, we're getting lucky today, aren't we? Okay. So I know 2x minus 1 is a factor. So what's the other factor? Remember, constant times constant must give me the constants. Leading term times leading term must give me the leading term. I've still got to work out on the right-hand side there, that second factor, how many x's we have, how many x squareds we have. We'll have a look and say, how many x do we have so far? At this moment, we got 6, we want 1. So I've got to subtract 5x. That would be minus 1 times 5. Could do the same with the x squareds. At this stage, how many x squareds do we have? I've got 5x times 2x, which is 10x squared, isn't it? And that's the only x squareds we've got. 10x squared, we want 5x squared, so that minus 1 must have been times 5x squared. Okay, we've got the second factor. I know there's another real solution in this one, so I could either apply the factor theorem again to the first one, or to my new second factor. Probably easier to go with the second factor. And obviously you'd go for minus 3 on 2 for the next one, and wow, that one worked too. So that became 0. So now I know 2x plus 3 is a factor as well. I've answered the first part. What are the two rational zeros? Well, half and minus 3 on 2 worked. Complete the factorisation. So I know we've got 2x minus 1, 2x plus 3. Leading terms, I've got a couple of them now. I need to get 4x to the power of 4. So I've got 2x times 2x. X squared must be in the third one. Constants, they've all got to multiply together. Minus 1 times 3 must be plus 1 in the second one. Now, how many x's? I can do a little thing on the side here. So at this stage, to get the x's, I've got 1 times 3 times 2x, that's 6x we've got. 1 times 2x times negative 1, there's another negative 2x. So it's 4x. We want to end up with plus x, we want to end up with. Couldn't find the original polynomial. We want to end up with plus x, so therefore we need another minus 3x. Negative 1 times 3 times what will give me negative 3x? That must just simply be x there. I left a little bit too much space. I was expecting a coefficient there. But all right, let's keep factorising then. X squared plus x plus 1. I'll complete the square on that. X plus a half squared plus 3/4. It's very tempting to multiply everything by 4, if you like, to get rid of those fractions. And if it was an equation, I could do that. But it's not an equation, so I can't do that. Because if all of a sudden I was to make that 2x plus 1 plus root 3i, and similar in the fourth one, when I expand out, I would no longer get 4x to the power of 4. I'd end up with what would it be? 2 times 2 times 2 times 2. I'd end up with 8x to the power of 4. Okay, if it's an equation, not a big deal. But that's not what we got. We just got a polynomial. So I would leave it like that. We're going to solve this equation. They've told us it has a root of multiplicity 2. Okay, you'll recall that if we've got a double root, then not only is it a solution to the polynomial, it's a solution to the derivative as well. What are my possible 45? Look at all the divisors 45's got. 1, 3, 5, 9, 15 and 45. The good news is it's monic, so I don't have to worry about the division. We could have negatives, of course, but at least we know what we're looking for. The derivative, that's going to come in handy. So my solution has to be a solution to both that derivative and the original one as well. And we're dealing with 1, 3, 5, 9, 15 and 45. The logical one to pick first is 1. But in this case, it didn't work. So 1 does not work, so we know that's not the factor. 3 works. By the way, once I checked out 1, I'm probably not going to check out 45 next. Because if 1 didn't work, probably its pair is not going to work. It might do, but probably better to go with 3. Safer to go with the smaller numbers anyway, they're easier to work out. And 3 works. For the derivative, got to work for the function as well. Oh good, it works for the function as well. We found our double root. We know x minus, or z in this case. We know z minus 3 squared is a factor. What's the other factor? Oh, leading term times leading term must give us leading term. At this stage we have z squared. Z squared times what will give me z to the power of 4? Z squared. Now let's look at that constant. So negative 3 squared is 9. 9 times what's 45? 5. How many z's do we have at this stage? In the left-hand one, even though I've written it as squared, it's actually got minus 6z there. Minus 6 times 5 is minus 30, and that's what we want. So it looks like it's factorised. We don't need anything else. Now the question said solve it. Okay, you could factorise it. I don't know why I bothered, to be honest, because because it said solve it. It didn't actually say factorise all the way down. So really, I could have just said z equals 3, and I had the z squared plus 5, so I knew that was going to be plus or minus root 5. I probably could have gone straight to that line. So 1G, but also some Patel questions, playing with polynomials, but now with complex numbers as well.